Hi, I'm Dave, KI4PSR. It's Saturday the 21st of January, the year 2012, and this is a reprise of the course we had 2 weeks ago about using the calculator to solve some of the more complex math questions in the extra exam pool. And really, you've had some really good instruction from Phil about the science and the math, science behind the math, and the beauty of the math. But so much of this is, you'd have to actually go to school for a couple semesters to really understand a lot of it. And what this is going to do is help you to answer the questions without memorizing the answers and learning the tools on the calculator, proper keystrokes, to solve these questions. And you might find then that you have more an aptitude for this than you thought. But we're going to start just by learning how to use the basic calculator as we did before. So if you go to the extra math tutorial paper I have here and get that out, and then the first page of the question pool. This question pool, by the way, was one that was online, and you'll find them online. I have the entire amateur extra question pool arranged in order the materials presented in the book, rather than in random kind of appearance inside at the back of your manual. You can get those online easily enough. But the first question we're going to use the calculator on is, actually we're not going to use the calculator right away, but we're going to talk about RC and RL time constants, because that will lead into questions where we will use the calculator. This is a very important question, and you guys who have been in Phil's electronic class know this by now. The RC time constant is the time it takes for a capacitor to be charged to 63.2% of its full value, or discharged to 36.8% of its charge. That's called one time constant. It's also called tau. There are 5 time constants from fully discharged to fully charged, or fully charged to fully discharged. So you have to remember there are 5 time constants, and that is what they call this term. And you should also memorize the values 63.2% and 36.8%. They add up to 100%, so if you know one, you know the other. But you will find some of these questions are going to be related to those very numbers, 63.2% and 36.8%. So the question at the bottom of the question pool, first page, what is the term for the time required for the capacitor in an RC circuit to be charged to 63.2% of the supply voltage? The answer is B, one time constant. That's a very simple question, but they're going to fool you. They're going to say, oh, a time factor of 1, an exponential rate of 1. They make it sound really one exponential period. You think you're, a scientist when you say that, but it is a simple one time constant. Question number on the next page, question pool, actually it says question pool page 19. The top of that is E5BO2. What is the term for the time it takes for a charged capacitor in an RC circuit to discharge to 36.8?
One time constant.
Same answer. Same question, just with a different approach. Okay. Now that you know that the magic numbers are then 63.2 and 36.8, the following question is going to be very simple. But you could do this on a calculator, but you can do this without even looking it up. E5BO3 asks, the capacitor in a circuit, RC circuit, is discharged to what percentage of the starting voltage after 2 time constants? Well, you know that after 1 time constant, it's gone down to 36.8%. Well, there are 4 answers here. One is 36.8%, so that's not it, because that's 1 time constant. The 2 above it are bigger, so they cannot be it. So without even bringing out a calculator, you can determine that 2 time constants is going to be discharged further and have less charge, so the answer D is the only logical answer. Okay, now it starts to get to the point where we're going to start using the computer calculator. Question E5BO4. Now we are going to start putting components together in a circuit. The RC time constant is a simple series circuit with a resistor and a capacitor, or a parallel circuit. What is the time constant of a circuit having two 220 microfarad capacitors and two 1 megohm resistors all in parallel? You need to know how resistors, inductors, and capacitors combine in parallel and series circuits. The 220 microfarad capacitors add in parallel. Capacitors add in parallel, divide more or less in series. Megohm resistances in parallel divide. If you have two identical resistors in parallel, their value is half the value of one of the resistors. So you need to learn that stuff as part of the general course and the technician course, but this is something you should learn anyway, and you should know this kind of information. You also need to know about units and the extensions. For example, microfarad. The mathematical term is 10 to the minus 6. It is smaller than 1. It is microfarad. Whereas a 1 megohm is 1 million ohms, or 1 times 10 to the 10th, to the 6th. So you simply combine the 220 microfarad, the two 220 microfarad capacitors to make an overall capacitance of 440 microfarads. The two 1 megohm resistors combine to make an equivalent resistance of 500K. And I say K, you can say 500 K ohms. These terms are going to be used a lot in this kind of work. But using the time constant formula of T equals R times C, we have an overall resistance of 500 K times an overall capacitance of 440 microfarad. Now you can do this on a calculator by putting in 500,000 times, using the times key, and you know you could figure this out and go 0.00044. You could do it that way, and you come up with the answer of 220 seconds. The units for this time constant is in seconds. But it's easier to use the exponential keys of your calculator. So we're going to practice with that first. On your calculator, put in 440. That's the 440. And you should have a key there that says EE. It'd be above the 7 key for most of these calculators.
I have it this time.
Okay. And you'll see a little superscript number come up on the upper right-hand side. And enter the number 6, because that's 10 to the 6. But remember, this is minus, this is micro. So you change the sign with the change sign key, which is just to the left of the equals key. Down, lower, lower. Got it? Yes. Oh, you were way ahead of me. That's okay. Now that, we have just entered the capacitor value there. 440 times 10 to the minus 6. Then the X key for multiply. And now we've got 500 K ohms. K meaning thousands, units 10 to the third. So 500, use the EE key, and then put 3. Don't change the sign now because it's larger than 1, and equals. And you got 220?
Yes. It works with the right keys.
Well, it's a lot easier. I might as well have had an Arab calculator.
Well, that was pretty unique last time. Now, you know, I actually use a different calculator for most of my stuff.
Don't change it.
No. These calculators have a second key where some of the keys have 2 functions. You can also find calculators like that have the third key. So I have some keys here of 3 different functions. And I use this almost exclusively.
Which model is that?
I don't know. Also, that's solar.
Oh.
What's interesting about this, if you know somebody's got a solar calculator like this, you know, and you want to play a joke on them, get some black electrical tape and cut it out just the right size of that solar cell and tape it over there and leave it on their desk. It's tried and true, works out every time.
I have one of those versions too.
Hey, can I see it?
Okay, but remember, different calculators will have different key labels for some functions that we're going to start to use, and some calculators have different dual or triple functions and use a so-called second or third key, and the second or third keys will be marked usually with the second number and also have some kind of color on them. Would you like to use this one?
Sure, might as well.
So you're going to have to learn how these keys work for your particular calculator. Okay, question number E5B05. This is on page 2 of my discussion and still on page 19 of the question pool. How long does it take? Now this is a little bit different, and I'm only doing this so we can use the calculator. But this is, you have to figure out percentages here, and this is basic math, but is not covered anywhere in their book. However, how long does it take for this initial charge of 20 volts to decrease to 7.36 volts in this time constant of the circuit made of a 0.01 microfarad capacitor with a 2 megohm or 2 million ohm resistor across it. So first let's figure out what the time constant is. We know we have 0.01 microfarads, so we enter 0.01, the exponential key, the EE key, 6 to get the exponent, and the change sign key to say, your display should say now 0.01 times 10 to the minus 6. So far so good? Mm-hmm. How about you, John? Mm-hmm. Okay. Then we're going to do the times key, and we have 2 megohms, so 2, enter 2, the EE key, and 6, because we don't change the sign because this is plus, this is above 0, and enter. And I get a time constant here of 0.02 seconds. How about you? Mm-hmm. This is going too well. Ken, you doing okay down there?
Yep.
All righty. So now we know what the time constant is. Okay. We find out, now you have to figure out what percentage of 20 volts is 7.36 volts. Well, divide 7.36 by 20. Let's just go ahead and do that. This is how you figure out the percentage. Divided by 20.
36.8.
Isn't that coincidental?
That's a miracle.
And they will do that a lot in these tests. Sometimes they'll have they'll have an answer like that. It looks like it's got to be right, but they put it deliberately in there as a wrong one. So just because it looks like it's right, don't assume it really is. But in fact, you're correct. In this question, the answer is A, one time constant. Is that correct? Yes, 0.02 seconds. Questions on that before I go on? E5B06. It's the same as above. The time constant in this case, let's measure it now. Let's put it in. You guys enter these numbers as we've just done and see if you come up with the proper time constant and figure this out. I'll just stand by and wait for questions. Y'all are still ciphering, but I'll tell you this is the same thing. So who got the time constant? Who has solved for the time constant? John, do you have the time constant?
Not yet, no.
Okay. The time constant is the multiplication of the R times the C. Mm-hmm. And the R, in this case, is 1 megohm, so that's 1 to the 6th. And the C is 450.
450, it's C.
So yes, you know that the time constant is 450 seconds by doing that math. But did you figure out how to do the percentage?
No.
Okay.
What does the percentage have to do with this when you're getting the answer?
Okay. They're saying how long does it take for the initial charge of 800 volts to decrease to 294 volts? So you've got to figure out how many time constants that's going to be. The time constants are solved by percentages.
Oh, okay.
So
Yep.
to make this easy, just remember to divide the small value by the large value, John. So take 294 and divide it by 800. And that is that's not a percent representation. To make a percent, you have to multiply that times 100.
Okay, so if your answer in a percentage of the voltage had come out to something different than 36.8, then it would be different than one-time constant.
Yes.
That I could figure out.
Right.
Got you. Okay.
Precisely, good.
Yeah, I'm back on planet Earth now.
I'm glad. John, don't despair. Can I help in any way?
No, not me.
No, I mean, so just remember the time constant, you multiply the resistance, you got that.
I've got that, yeah.
The problem you're having is with the percentage?
Well, I'm just, yes, the percentage and why do you subtract the higher number from the lower?
Or divide, yeah.
Or divide.
Yeah.
I'm trying to make sense of, is
Well,
that
it's
a
really
rule,
is-
or is that?
I find these ones are, you've got to sort of, I have to step back and think about it from the time constant as though I'm doing the problem in the other direction.
Yeah.
And so I think, well, if it's one time constant, it's going from the higher voltage, it's discharging down to the
Okay.
lower voltage. What is the percentage change in voltage? And then is that, if it's 36.8, then that's one time constant. And then you're figuring out what the time constant is from the resistance and the capacitance.
Yeah.
Is it one time constant, two time constants, three?
So the only reason that we're dividing the
Yeah.
voltage at all is to determine, is to make sure that we have one time,
Like I-
constant,
yeah.
not two or three.
Find the percentage, yeah.
Right,
Yeah.
okay.
But don't despair, because these questions here are all the questions in the various question pools. Your test may not have either of those questions.
You may have both.
You may have both. But you now have been exposed to how to solve, at least know how to do time constants.
Yeah.
And from there, you can probably determine what to do. So but yeah, don't despair.
At least now I know what a time constant is.
Yeah.
I'm doing better than I was 10 minutes ago.
Yeah, and it's really fun if you're trying to make a circuit that will, let's say, trip a relay at a certain voltage. I'm simplifying here, but you can make a time constant out of a resistor and capacitor and a coil, and you put voltage to it, and you can time how long it's going to take for that capacitor voltage to raise high enough to close the relay.
Yeah.
So it's got some practical stuff for the home experimenter. Okay. That was essentially to get you comfortable with the calculator and to disturb John. Oh, I mean, now we're going to talk about this whole thing of phase angle and complex numbers. In my experience, the people who are going for extra, who do not have a strong math background or electrical engineering background like I have, and like David has, like Joe has, this stuff is just complete gobbledygook and Greek, and I think it's put in here to give you an appreciation for what the scope of some of this stuff is, but also it's a rite of passage. And some people will try to memorize these and be successful at it, but there's no point in having to memorize it. If you can just learn how to use the calculator, you will actually have a lot more fun in the future. And it's great at parties. Yes, you go into a party and say, well, what do you, anyway, so showing expertise with the calculator is also great fun.
You go to strange parties, though, do you?
Yes, I do. I come from a strange family.
Okay.
Yes, we used to solve quadratic equations around the supper table.
Sounds like my dad.
Actually, we didn't.
Well, my dad's a math professor.
Okay, let's see here. Let's go to page 20 of the question pool. And we're going to talk about Eli the Iceman. This will be the third time you've heard about him in these courses, whereas we also talked about it a bit in the electronics course. The simple mnemonic method for learning how current and voltage are in phase or out of phase through capacitors and across capacitors, through capacitors, and through inductors. ELI. E stands for voltage, L stands for inductance, I stands for current. Eli. The E comes before the L, the I comes after the L, I comes after the L. So voltage leads current in an inductor. You can also say current lags or is behind E in an inductor. ICE is a similar technique. Current leads voltage in a capacitor because it's ICE, and voltage lags current in a capacitor. These will, generally speaking, always be 90 degrees, never more. So, question E5B09. What is the relationship between the current through and the voltage across a capacitor? the first thing you know is they're talking about a capacitor. So you know it's going to be ice. Well, you got it?
Yeah.
You got the answer? Oh,
Chip off the old block.
yeah. I thought you looked like Jack for a second there. Yes, sir? You had a question?
So why 90 degrees? Why not 85?
Well, that's a question you're going to ask Phil. I'm not here to answer that question.
Okay.
Now, I don't want to get involved with that. I want to get involved with this. But he had a good representation. You were here when he was up there at the blackboard.
Okay.
But
Yeah, probably have it in my notes.
call him up. I don't want to embarrass myself by trying to pretend I know how to answer that.
I don't suppose you have any additional reading that would be fun to learn this.
Yeah.
To really put it,
Well, it's called electrical engineering. You can go to school for that.
well,
Well, there's the, that textbook, the, one of the ones that I had on my list,
That's right. The list he sent out when you were in the electronics course. Yeah.
Hill and, Horowitz and Hill. It's, is it Cambridge or, no, Cambridge Press, I think, but it's, I can't think of the title of it off the top of my head.
Okay.
Well, frankly, I don't want to bog people down or get you really confused or actually discouraged by going through anything more than handling the math at this particular course.
okay.
Today, if anybody doesn't have it, the ARRL handbook, which is also available in searchable PDF format. So now that everybody has computers, you get the PDF of that on your computer, and you can search for terms like that phase angle, and a lot of times you come up with stuff that's eliminated.
It is fun.
It says in this book here, just real briefly, for pure reactive, no resistance, the phase angle is 90 degrees. So no resistance is purely reactive, it would be 90 degrees.
Yeah, that's very sharp. That's a very sharp cue. Once you start adding resistance, the cue starts spreading out and the angle changes. But that's, again, I don't want
That's
to.
right. Okay.
Okay.
I'm back.
Okay, good. Question E5B10. What is the relationship between the current through an inductor and the voltage across an inductor? Now, that's very good, Eli.
Eli.
So now we'll be using Eli the Iceman for solving the rest of these questions. So if you'll remember that mnemonic, you're good to go. Okay, page 3 of my notes. And we're still on page 20 of the question pool. And we have 1, 2, 3, 4, 5 questions that are all asking about phase angles. Phase angle is a question they're going to ask you, and you have to figure out certain aspects of the circuit. But we're talking now about capacitive reactance and inductive reactance and pure resistance. Reactance, capacitive reactance, for example, is the amount a capacitor wants to impede the flow of electrons at a certain frequency. And inductive reactance, of course, is the amount of resistance, if you will, or impedance that the inductor presents at a certain frequency.
Sorry.
That's all right.
Email.
The term for capacitive reactance is XC, X sub C, but X stands for reactance. So when you see, they say X, question 7, for example, they say X of C is 500 ohms. Capacitive and reactive inductance has the units of ohms, They tell us that the resistance is 1 kilo ohm or 1,000 ohms, and X sub L, the inductive reactance, is 250 ohms. The capacitive reactance and inductive reactance do something, they add in a form they add algebraically. But you don't have to know that. Always, when you're looking at a question like this, subtract the smaller reactance from the larger reactance to get the overall cumulative reactance. So we have 500 ohms of capacitor reactance and 250 ohms of inductance reactance. Well, 250 ohms of the capacitive reactance is canceled out by the 250 ohms of the inductive reactance. We are left with a net of 250 ohms capacitive. You copy that?
Copy. I'm still trying to figure out why we automatically do a subtraction of the smaller one from the bigger one?
Here,
Well, in this example, and then the division.
the division was finding percentage.
Yeah.
And that's a math question. And so study percentage,
Okay.
calculating percentage when you get home on a math book.
Yeah, okay, I got that. I guess I'm thinking about it in the context of,
But this is a different problem entirely.
yeah.
Here we have one reaction that's going this way, here we have going out that far, and here we have another reaction that's going this way, going only half that far. So you take them all back, and we only have reactions going out this far.
Okay.
So now we know now that we have an RLC circuit, but it's really mostly just 250 ohms of capacitive reactance and 1 kiloohm, 1 k ohm of pure resistance. We are going to now, let's see, I'll get grounded again here. So we know that this is going to be an ICE problem. You need help?
What was XL again?
XL was given to us to be 250 ohms. This is
Like, what does it stand for?
inductive reactance.
Okay.
Yeah, L is inductor, C is capacitor.
Yeah.
So we now know that this is going to be an ICE problem because we have really 250 ohms of resultant capacitive reactance. And we know that the voltage lags current. Well, hang on a second here. I got some bad text there. I have inductor, what I should say capacitors, that kind of thing, and leads. So I'm going to redo these for the next year after the new question pool comes out. But if you find stuff like that, let me know. But Bill, thank you. Oh, there's just a misleading sentence, but it's not misleading, but it's just not pertinent to this question. But we know that capacitance current leads voltage in a capacitor, which is equivalent to saying voltage lags current in a capacitor. The term inductor there is wrong. At any rate, but pay attention to the tricky wording they have here. Sometimes they'll say leading, sometimes they'll say lagging. So you've got to really pay attention to that. Now then, I've got to figure out where I was. Okay. You could solve this question, half of this right now, you could solve because you know that the current is leading the voltage in a capacitor, ICE. So the only questions here, the only answers that are valid are the ones that say current is leading voltage, or voltage is lagging the current. I'm trying to get grounded. Okay, now let's go to the top of page 3, and we'll start using this with the calculator. We've already taken 500 ohms. Let's go to the second paragraph in my instruction sheet here.
Okay.
We've already taken 500 and subtracted 250. I jumped ahead, John. I'm sorry for getting...
No, you're good.
Okay. The questions are asking for phase angle, and we have to now convert this rectangular representation to polar form to get the degrees. There is a button on your calculator called tan to the minus 1. It stands for arctangent. It stands for phase. It's used in calculating phase. You don't have to memorize this, but here it is. Phase angle theta equals tan to the minus 1 of the reactive component divided by the pure resistive component. But all you really have to do here is first divide 250, that is the cumulative reactance, by 1,000. Always divide the resistance by the, the reactive component is above the line, the resistive component is below the line. So in this case, 250 divided by 1,000. And you get 0.25. And now, you're going to have to use the 10 to the -1 key. Now, you will probably find this is going to be a alternate key press calculator button. And if you solve it, I want everybody here to tell me they got 14.
I actually got 14.036.
Mhm.
34.
Now, what's going to happen too in a lot of these questions, I've noticed this in the question pool, your answers that you get here in the calculator are right, but the question pool will not have them exactly the same way. I don't know why that is, but you know, typos happen.
This question, I think, is illustrating Sharon's law. If there's a 14 in the answer
Yes.
pool, it's one of those two. You just have to know if it
That is
leads
Sharon's
or
law.
lags.
Yeah.
Yeah,
Yeah.
because Dave spent a lot of time on that.
Yep.
Yeah. Oh, that's right.
No, you can.
Well,
Other misnames going on.
but so we know the answer is 14, and now we have to know which of these 14s. There's two 14s, B and C. And you know now it's ice because it's capacitive. So guess what? The voltage is lagging the current, is it not? So the answer is C. Okay, and I also write here, notice that the result is essentially 14. You can use the same technique to solve for the phase angle of all these questions. However, notice that in every case, the answer is 14. But if you'll do the math, using the arctan key, you won't get tripped up. But the truth of the matter is, and I hate to, I mean, anybody running these sets of questions like I have over and over again, you'll notice that they're all 14. And all you have to do is apply Eli the Iceman, and you're done. Let's take the second one, E5B08. We have a capacitive reactance of 100 ohms and an inductive reactance of 75 ohms. So we have a net capacitive reactance of 25 ohms. Is that correct? Mm-hmm. We know it's capacitive. I'm going to do this again using the calculator. So we say 25 divided by 100. We divide the reactance component by the pure resistive component, and then apply the arc tangent key on that, the tan to the -1.
14.
That's amazing, it's also 14. Does it divide the, okay, we have a reactive, resultant reactive component, capacitive reactant component of 25 ohms, and you divide that by the real resistance, or the pure resistance, and we have 25 divided by 100, and then we take tan to the -1 and get 14. Did I say that right?
You're doing something wrong.
Okay.
With 36.
Okay, first of all, okay, are you using the second key before the tan?
Yes.
Okay, so you divide 25 divided by 100.
Oh, I think the reason I'm wrong is I'm on the wrong question.
Yeah, that
It's
happened.
amazing how that will work.
That's happened.
Let's try this again.
That's happening to me, just sitting here, and this is the third or
But I have to
fourth.
say, with these two types of questions, I go with the graph, and that you don't even need to pick up the calculator. It's that same process of elimination. You can sort of look at the angle and say, well, it's less than 45, so.
Well, you've got the brain for that. This is what I rely on. And I really admire that, and admire what Phil's done with that too.
Yeah. No, I found that very, very.
Okay, have you divided 25 by 100 and got 0.25?
Yes.
Okay, then press the alternate key to get tan to the -1 of that.
Oh, okay, 14.
Amazing. Now remember though, we had a overall cumulative reactance that was capacitive at 25 ohms. So again, this is an ice. So here are two questions, and one says voltage lagging the current and one says voltage leading the current. Well, voltage E is lagging in a capacitor, so the answer has got to be A. Eli the Iceman and 14 degrees.
Okay, I'm so caught up on the math part of this. How are you using Eli the Iceman to figure that out?
Okay, well,
You just said it, but I kind of
that's fine, that's good.
5 steps behind you.
They're talking about a circuit here that has an inductor and a capacitor
Yeah.
and a resistor. And the inductor has some reactance, and the resistor has, the capacitor has some reactance.
Yeah.
And let's say that they are going in completely different opposite directions.
Yeah.
You add them together or subtract them. You subtract the larger one from the smaller one.
Yeah.
Okay, let's pretend they're apples and oranges.
Great.
Huh?
Great.
Good. We have, in this case, we have 100 apples and 75 oranges. If we, that doesn't, this is a bad one.
Well, you're gonna have more apples.
Yeah.
than
Yeah, we got more, but that's,
On balance, you've got more.
Okay,
I
so
mean,
you got more
I find it
reactance.
easier to always think of capacitive as negative.
Okay.
And so that it's just, you add the two together,
algebraically.
whatever's left
Yeah.
Well-
is, if it's positive, it's inductive, if it's negative, it's capacitive.
The point I want to make, though, is that you are going to have an overall effective
Yeah.
capacitance rather than inductive.
Right.
Do you see that?
Because the value ends up being.
So this really can be boiled down to a capacitor of capacitive reactance of 25 ohms and a resistor. You see that?
No.
Okay, we've eliminated all the X sub L by 75 ohms of the X sub C.
Yeah.
They cancel out. So now we only have X sub C of 25 and R of 100 ohms.
Yeah.
That does make sense.
Yeah.
So now you see that this circuit has no inductance left to it. It is a capacitive circuit.
Yeah.
And that's how we use ICE.
Okay. Okay.
Because C is for
It's
capacitive.
negative.
Right,
That does
yeah,
help a
because
little
it's
bit.
negative and therefore C, that's the ice,
Yeah.
part of Eli the Iceman. Well,
If it were
and Phil's-
positive, we could use it. And
Yeah, I don't know whether it was you or Phil that came up with it, but the idea that Eli gets hot carrying the ice, hot is positive, cold ice is negative, is the
That
other
kinda sounds
handy
weird.
thing to,
Well, but it's just so simple to say, take the larger one from the smaller one,
Yeah.
and the larger one's the dominant one.
Okay.
The larger one's the dominant one.
Yeah. Okay. I see
yeah,
that
that's a
now.
good, that's, yeah.
And in this case, are we on 12 or 11?
Well, let's go to 11.
Okay.
Now, tell me,
Yeah, we were on.
John, is this a overall capacitive reactance solution or overall inductive reactance solution?
Inductive.
Precisely. And inductive is Eli.
Yes.
So which of the two answers is it going to be?
It would be leading,
The voltage leading,
and it would be 14 because 14 is the magic answer on all these.
yes. So you can solve every single one of these questions now just by knowing Eli the Iceman
Yeah.
and
Well,
14.
Yeah, and the other thing you notice too is that they're all a quarter, because it's all 1,000 and
Yeah.
250 or 125.
Oh, that's a good perspective.
Yeah.
When we first start the test and sit down, can we take a piece of paper and
They
start
give you a
scribbling all
Yes.
over?
One-
You
one-
can take something.
You can't bring it in there with the scratching on it, but once you
Well,
sit
yeah.
down, you can write all the equations that you can remember.
Well, now, the book said that if you have a disability, you could use a computer.
We know you. We know that you are.
I'm sitting beside you.
We know that you are brilliant, and we don't have to worry about you passing the test or not. And you don't need that kind of help.
You're in trouble now.
No, no.
Okay. So what, are you guys laying odds on this? There's like a pool going?
You know, some people do very, very well in these tests, and other people clam up and freeze up, and there's no reason to feel thwarted if you don't pass it the first time. Some testing sites will allow you to take this test over again without any paying it again. If you, in our test site, you will have to pay the entrance fee of $15 again to take the test over again. But I assure you, if you go through these tests like online and do these questions as I explained here with the calculator, you'll be so comfortable with it, you won't have to worry about it. But yes, if you want to memorize these equations, and when you get them there before you freeze up and get all thwarted, write them down when the session starts. You'll have to turn in that scratch paper when you're done. Don't forget to do that. I want to try the last one, E5B13, which is it, we have 250 ohms capacitive, 500 ohms inductive.
Inductive.
Precisely. There's no, you guys have got this. How are you doing on that, Ken?
XL, it's inductive.
Yeah. Are you feeling comfortable with that?
Pretty good.
What's got you uncomfortable about that?
Well, I guess sometimes I'm trying to realize the formula, and I don't see the formula when I'm working on a calculator, so maybe I should forget the formula and just,
Well, yeah, the only formulas you need to learn with this one are subtraction. You subtract the large one from the small one to find out what's going to be Eli or ice.
okay?
But to get the angle, the number 14, all you have to know is that this is a function using the tan, the minus tan. And in that case, you always put the reactance in the calculator first and divide it by the resistance, then hit the minus tan. So, for example, this one, we're going to wind up with an overall inductive reactance of 250 ohms. So I say 250 divided by the resistance is 1 k ohm. You can put in 1,000, or you can put in 1 e to the 3, to the third, and you get 0.25. Then you have to do the arc tangent on it. That's the tangent of -1. And manipulate the keys to give you that. And once again, it is 14. But Ken, on all these questions, and these are all the ones where they give you the capacitive reactance and the inductive reactance with these 5 questions. And the answer to all of them, of course, is 14. You will not get all 5 questions on the test.
So that sucks. 'Cause it'd be handy.
Yeah, now that I know
Yeah,
how
because
to
then there
do
wouldn't
it.
be any of the policy ones. We can get the math down, we're good to go.
But practice this with each one. I know you know it's going to be 14, but if you'll do this and use a calculator and divide the reactance by the resistance and do the tangent of -1, it's a great trick at a party. Okay, let's go on to page 4 of my notes and page 21 of the question pool. Now then,
What's the question number?
we're going to talk about E5CO1. Do you need a question pool?
No, I'll just follow along in the, I mean, if you've got your updated one.
Yeah, I've got them. I've got plenty of them.
Just one, before we leave that.
Yes, sir.
1 second. You said you divide the reactance by the resistance.
Yes.
All right, would it be safe to say you divide the dominant reactance
Yes.
by the resistance?
Yes.
Did I heard that correct?
Well, no, you have the resultant's reactance.
Or so the results of subtracting the larger from the smaller?
Yes, sir.
Okay, and then divided by the resistance.
Yes.
You would subtract the smaller from the larger, so 500 minus 250.
Yeah.
You would end up with 250.
I said it backwards.
You divide that product by 1,000, 1 kilo ohm.
By the resistance.
And then you do the tan one.
Yes.
I have to say, the thing that,
Go ahead.
just that I find confuses me, because it's then I have to remember whether it's, I have to think harder about whether.
That's because you have the scientific and engineering background that these people don't have, and they don't have to have that. But what we're trying to do now is allow them to solve these questions. Okay, if the general course, extra course I should say, I don't know why these questions are in here, and Jack said they weren't in his, but if they were requiring, if the ARRL was requiring for you to know what you know about this kind of stuff, you would have to go to engineering school. You could not do this on your own. You would have to be a bloody genius to do it on your own.
Well, thank you.
You're very welcome. The fact is, this is a rite of passage.
What is it?
It's hard work, that's for sure.
It's really enjoyable to me.
Yes, it is.
But if you'll, okay,
That's why we're here.
Just the rectangular plot, basically, but then converting it to polar.
Ken, are you understanding? Because it took me
I
a
just
while.
want
And it
that
basically
first
lets
part,
you-
still, what you just said, I'd like to get that written
But
down
if you
so I
do the
know.
math.
You subtract the larger from the smaller.
yes.
Reactance, the angle is
Big
I'm
number
dividing
minus
the wrong
the
thing by the wrong
We want to
thing.
end up with a
45-degree angle,
positive.
because
You don't want to
this
end up
axis
with
is the same
negative
value as this
250.
axis.
Okay, so in
it's
that
like
case
1
on
and
13,
1,
you
so that's
subtract
right, 2 and 2, 3
500,
and 3,
that
and
gives
so
you
on.
250.
Yes.
You can
Now,
then say, well,
now
if the
divide
resistance is
that
Coming out
larger
with
by
than the
36.
The
reactance,
meg on.
you know,
I'm
you
doing
can
something
say it's
wrong.
going to be less than.
In this case, it's 1 k ohm, yeah.
On the 12.
And if
Yeah.
if it's the other way around, the reactance
So I'm
is greater than the
dividing-
resistance,
Yes.
you know, the resistance was say 2 and this was 10, the point's going to be over here, so it's greater
It
than
would just be
4,000.
10, 1.
I think
and
you very
then
quickly
divide
eliminate.
That would be 14.0.
divided by,
I'm going back and do 250 divided
But you're
by
right,
1,000,
it's
so I
it's
get
really how
1,000.
you approach it, it's whether
And
you
do
think about
equal.
it that way or
That's
think about it.
0.25, then you do second
coming up with 0.75.
14 going up.
That's it.
Let's see.
And you would always subtract.
Oh, it's out there.
One is 37.
His background.
Am I doing the wrong
Out there.
value?
My
Should I
background.
divide it?
Oh, okay.
Eli or ice.
Right, I got
You
the
know,
eyes
it's
for
funny
our
you
people,
mentioned
that's
doing this at
subtract
parties.
the
My
smaller
parties
larger
usually
people.
involve guns.
Would you
I got it right.
But not
No,
all.
it's kind
Which
of
is why we were
I'm
late.
trying to think
Because
now.
you're always putting the more.
That's true.
The bigger
Yeah.
number.
You and Scott were having a party about
It's
bullets.
greater than X,
Well, it's
so
6.8
it's
SBC.
past
It doesn't
it.
make a lot.
Yeah, I mean, it's.
Now I gotta-
Thanks, John.
He's one of the co-designers.
We'll get there.
Well done.
We're all in this
So
together.
it's all his fault, with the deer arm.
I'll go blame Steve.
Can we
Okay,
be
thank you.
boring, Dave, and
Yes.
please go back to one of the questions?
Sure.
12.
E5B12.
Okay, what'd I do wrong?
I don't think you did. I keep coming up with 3.6 point blah, 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 blah.
Okay.
And there's no 3.6 for an answer. What am I doing wrong?
Okay, what is the phase angle between the voltage across and the current through an RLC circuit if X sub C is 75 ohms and X sub L is 50 ohms, R is 100 ohms? So we have 75 ohms of capacitive reactance and only 50 ohms of inductive reactance. So we should have 25 ohms resulting of capacitive reactance. And say 25 ohms divided by 100 is that pure resistance. As again, to 0.25, and we do 10 to the minus 1 on that, we get to 14 again. So that's done. So we know that it's 1 to 2 14s, and the overall,
Capacitance is bigger, so it's ice. So, and then it's lagging.
So let's, Laura, go through the,
yeah, Laura,
I'm doing something wrong here. I'm dividing 75.
no.
No, you gotta find the product.
there's your, you've
Oh,
got
okay,
to
then I'm
find what's
getting that
left.
stuff.
I did
Yeah,
that
you've
earlier.
got to figure out what's
Look
left.
at you, man, you know,
So 75 plus 50 is the
Yeah.
25? Okay.
You're gonna subtract the smaller number from the bigger number. So in this case, 75 minus 50.
Okay, so that's for the
Capacitance.
25.
That's the
Yeah.
25.
That's where
You're
your
dividing by
25.
100.
And then when you divide that 100, you get the 0.25, like you have in all the others. That automatically
I did that wrong too.
Yeah. But I would argue, I don't know, I find that 14 thing a red herring. You know, it's like you don't even need that. You know, so once you get the basic math, it's.
Then you get
yeah, all you have to do is you can just look at these, and you know it's 14, you can just say which is Eli. All you have to do is simple subtraction, and you can solve all these, but
Well, and if you're good at,
Here,
Okay.
I would argue
75.
even if you're not
75.
good at the engineering, if you
75.
just
And you
know
know
the
where we
basic
got
math
75?
plots, you don't even need to
Okay,
calculate.
and now we're gonna
You know
subtract
whether it's lagging
50.
already.
Yeah, you
Which
just
is,
look
you
at
know,
where it
it's
is
gonna
on the
be-
graph.
On the
and-
45.
Yeah, so that equals.
Like Phil did the great
25.
thing with
Now
the,
divide the 100.
where is the,
Yeah.
the R versus the
100
X
divided by
on the
25.
graph,
No,
is
no, no,
above the
25
45 or
divided by
below the
100,
45.
and that's gonna give you 0.25.
Okay,
Okay, now if
0.25.
you do your tangent, that's gonna end up with 14.036. Yes.
Which I got the right thing.
So you got 14, we kind of know that's a given, but now we got to figure out whether it's Eli or ice,
Right,
and the capacitive is the bigger number, so we know it's going to be lagging.
right, okay. Yeah, I got
There
it
you go.
once.
he came from nowhere.
Okay, good.
That's 0 to 150 in
That's right.
3 seconds.
So X.
Yeah, the trick
L
is
the
what you were getting at earlier, that the X and the L cancel each other, and so it's what's left. So you've
Okay.
always got to do that subtraction.
But you know, there's that trick question where you can say it differently than the answer there.
Yeah.
Yep,
And
yep.
say the current's leading the voltage.
You got to watch out for that. They're really bad actors in that
I
regard.
had one on my general like that, and I just slapped my forehead. I knew it. I was just.
Well, you know, the thing is too, that when you take the test, this is a 50 question test, but you've got all the time in the world. When you've done it, when you're done with it, go back and do it again. Every single one of them, look them over. Because, I mean, I do that all the time. I have dyslexic moments.
Yeah.
I've read the question and read the answer
Oh,
wrong.
yeah.
Don't give one away, there's no time limit.
Yeah.
Now then, we're going to talk about rectangular coordinates and polar coordinates. And one thing they will teach you in the book is the way to express a impedance in rectangular notation. Impedance is the combination of resistance and either capacitive reactance or inductive reactance to impede the flow of electrons at a certain frequency. The certain frequency determines the reactance component. So we're going to be talking about impedance. When you talk about impedance, you do it in ohms as well. But impedance, it has to be expressed in two components. One is the pure resistive component, and then plus or minus the reactive component. Now here's where what David was saying becomes very important. The series representation, the rectangular representation is Z equals a pure resistance value plus J or minus J. J is an imaginary number. Imaginary number operators, don't worry about what a J stands for. Plus or minus J, and then the amount of reactance in ohms.
There's no idea how a bunch of bugs me that I don't know what J is. So.
It's an
John, it's electrical.
It's a square root of -1.
Okay.
Try
It
it.
is.
Try
It
it.
is weird.
That makes sense.
1, change the, and take the square root of that.
The
Error.
fact that our math has that kind of stuff built into it.
Error.
Error.
Yes.
It's imaginary.
Imaginary.
And this right, I want to start off right on this one. At Z equal 100 plus J 100 ohm.
Yes.
Plus minus.
So why'd they
It's
put it
supposed
in
to be
there to
plus or
start with?
minus between that?
No, no.
My question. Why'd they
If the reactance component is inductive,
It's an error.
it's plus J.
Why did they put it in there to start
If the reactance component is capacitive, it's minus J.
But on like BO7, it's capacitive, right?
Say that again.
On question BO7,
BO7. Are we go back page?
page 20, from question B, E5 BO7,
Okay, we're,
where we're at.
no, no.
We're moving on to the-
We're at page 21 in the question pool, page 4 of my notes, top. So,
But Jim, make sure you identify where I'm having a problem with that. When I see that formula, it looks to me like there's, needs to be an answer. And there's no answer, so Z equal 100 plus Joule 100 ohm.
it's not joule, but go ahead.
Now what?
It's J, it's not joule.
Not Joule?
It's not a joule. Joule's power. This is an imaginary number. If you were working in terms of pure mathematics, they call it minus I, lowercase. But because we have a I for current, the electrical people, we like to have it as a minus or plus J, lowercase. This is an expression of impedance in rectangular coordinates. It is an equation, but it will be solved in just a few moments here.
Okay, so we're supposed to take that and replace the 100 and the J100 with the numbers in the problem?
Yes, we are given this, well, we're given the data in the question so that we can write this formula out.
Okay,
And then we're going to use the calculator to solve this because they give us the impedance in rectangular form, but they want it solved in polar form. And again, without trying to duplicate what Phil did or confuse anybody, let's just remember there are two forms they're going to be talking about, rectangular and polar. The expression for rectangular coordinates is given by this expression on page 21, or page 4 of my notes. They tell you they've got a 100 ohm resistor, they tell you there's a 100 ohm reactance, and they tell you it is inductive because it's a 100 ohm reactance inductor. So we have to memorize that inductive reactance is plus, capacitive reactance is minus. So the way this is written then is, as I show on the first sentence of page 4 of my notes, Z equals 100 plus J 100. That is because it is an inductor. So you need to not only memorize Eli the Iceman, you need to memorize that inductors are plus. And then the expression he used for figuring that out from Eli the Iceman, I never quite got that, climbing up the stairs with the ice on, getting hot and cold and all that kind of stuff. Please memorize,
Well, it's a no-brainer, it's easy. If you've already got Eli is the Iceman, he's a guy carrying ice around, so it's a natural.
And the ice is gone.
And I mean, the advantage of doing the graph is that because you know it's 100 and 100, the angle is automatically 45 degrees. You
Now-
don't have a calculator at all.
Here's something, and we can take a break if anybody needs one.
And
I have this room reserved for one more session next week. If you want to present your method of turning.
No, this was all Phil. I mean, I like the combination of the
Okay.
two approaches. It's,
But it'd be good to have a third.
That's why Phil
I-
had said, go ahead and write out the graph, and you can just, by process of of elimination.
You are
the
you are getting much better grounded that way,
yeah.
and maybe you'll actually be able to use that at some point.